Now we move on to the multiple angle formulae, which are the trigonometric ratios of the multiples of some given angle theta. So it's like 2 theta or 3 theta and so on. So we derive for only some of the most commonly used results. So firstly we have the derivation for sine of 2 theta. Now this we can write as sine of theta plus theta, isn't it? And using the expansion for sine of a plus b, we can write that as sine a cos b plus cos a sin b. Interestingly, since both a and b here stand for theta only, we get both the terms as same, that is sin theta cos theta. So adding, we can write 2 sin theta cos theta. So the first result is 2 sin theta cos theta. That means if you have sine of 2 theta, that can be written as 2 times sine of theta and cos of theta. So you see the angle which was 2 theta earlier, now that gets halved, that becomes theta now. So instead of 2 theta, if it were say 4 theta, suppose we had to write sine of 4 theta, I can merely write that as 2 times sine of 2 theta into cos of 2 theta. So the idea is that angle becomes half. Suppose we had originally the angle itself as theta, then that can be written as 2 sine of theta by 2 into cos of theta by 2. Now it can be easily proven that 2 sin theta cos theta can also be written as 2 tan theta upon 1 plus tan square theta. So that is sin 2 theta can be expressed in terms of tan of theta also, and we can easily prove this with the help of known identities. That is, if you look at the denominator, 1 plus tan square is nothing but sec square, so we get 2 tan theta upon sec square theta, and converting into sin and cos, we will get back the result 2 sin theta cos theta. So that's the way to get the expression for sine of 2 theta. Let's move on to cos of 2 theta, which is a very important result which we'll be using most often in many places. So let us see how we can derive the expression for cos of 2 theta. There are 4 different forms which can be derived for cos of 2 theta. The first is like this. Initially we write 2 theta as theta plus theta like we did for sine. So using the formula for cos of a plus b, we can write cos a cos b, that is cos theta into cos theta, minus sin a sin b, that is sin theta into sin theta. So clearly that can be written as nothing but cos square theta minus sin square theta. Now we can modify this further. That is, suppose we want to write the entire expression in terms of sin theta only, then we can write the first cos square theta term as 1 minus sin square theta. We merely replace it, and minus the second term as it is, that is sin square theta. So that ultimately gives us another result, that is 1 minus 2 sin square theta. Now instead of sin theta, we want the entire expression in terms of cos theta. Then what we would do is, the sin square theta term we will express as 1 minus cos square theta, isn't it? So therefore we'll get another expression, that is 2 cos square theta minus 1. So cos 2 theta is equal to cos square theta minus sin square theta. It is also equal to 1 minus 2 sin square theta, and it is also equal to 2 cos square theta minus 1. Alright. Now based on these, we have 2 deductions which are also very useful. That is, 1 plus cos 2 theta is nothing but 2 cos square theta, which comes from rearranging the terms of 2 cos square theta minus 1 merely. And if we have 1 minus cos 2 theta, that turns out to be 2 sin square of theta. Again, this form is very useful and is often used in many examples later on. There is a fourth form also, whereby we can express cos 2 theta in terms of tan of theta. So let us see how to do that. We start by writing cos 2 theta as cos square theta minus sin square theta, which we just proved. Now what we do is another intelligent trick here, that is, since denominator is not written, that is nothing but 1, which is always present. So we have cos square theta minus sin square theta upon. Now we write this 1 as cos square theta plus sin square theta, because that's a fundamental identity. And then if we divide both numerator and denominator by cos square theta, we will get 1 minus sin square theta upon cos square theta is nothing but tan square theta, and upon 1 plus once again tan square theta. So this is how we get the fourth form of writing cos 2 theta in terms of tan of just theta, that is, the angle is half. So this is the half angle formula for cos of 2 theta. Let's go ahead to the double angle formula for tan 2 theta. Now we know the expansion of tan of a plus b, so on similar lines we write this as tan of theta plus theta, and tan of a plus b is tan a plus tan b, that is tan theta plus tan theta, upon 1 minus tan a into tan b. So here it is tan theta into tan theta, because once again both a and b are same as theta. So that ultimately gives us 2 tan theta upon 1 minus tan square theta. So this is the formula for tan of 2 theta. We move on to the triple angle formulae, wherein instead of 2 theta now we have 3 theta, but the procedure is very much similar. Now here 3 theta can be expressed as sine of 2 theta plus theta, right? So therefore on expanding we get sine 2 theta cos theta plus cos 2 theta into sine theta. Now our aim is to try to express the entire right side in terms of purely sine theta. Right? Now to do that, let us first write sine 2 theta as 2 sine theta cos theta. But since we have one more cos theta term sitting, so I can write the first term as directly cos square theta, plus cos 2 theta can be written as 1 minus 2 sine square theta, which we have just seen, and multiplied by the last term sin theta as it is. Now since we want to see everything in terms of sine, I must replace cos square theta by 1 minus sin square theta. So therefore doing that we get 2 sin theta into 1 minus sin square theta plus, now let us expand the remaining term, that is where we get sin theta minus 2 sin square into sin will give us sin cube. So expanding the first term, we have 2 sin theta minus 2 sin cube theta plus sin theta minus 2 sin cube theta. So therefore on collecting the like terms, that is 2 sin theta plus sin theta gives us 3 sin theta, and the remaining two like terms, that is minus 2 sin cube minus 2 sin cube, that gives us minus 4 sin cube theta. So this is the last expansion, that is the last statement, is the required expression that we are looking for. So you see the right side is entirely in terms of sin theta. So what it means is, if we know the sine of some angle, we can calculate the sine of 3 times that angle. So that is why we had the purpose of expressing the entire right side in terms of a single term sin theta. Now the procedure to calculate expression for cos of 3 theta is also very much similar, that is we express 3 theta as 2 theta plus theta and solve on the similar lines, which we won't go into that because it's on the same line, and ultimately we will get the expression of 4 cos cube theta minus 3 cos theta. So if you compare with the previous expression, the sine cube was present in the second position and sine theta was present in the first. So in case of cos, it has reverse, that is cos cube comes first and cos goes to the second position, and the terms, the coefficients are also interchanged. In case of sine 3 theta, 3 was in the first position, but now here we have 4, and earlier when 4 was in the second position, now we have 3. So that's the way to remember the formulae by comparison. And let's see the last result of this group, that is tan of 3 theta. Once again we express this as tan of 2 theta plus theta and solve further by writing the individual formulae, and at the end we get the result as 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta. So that's the formula for tan of 3 theta. You see the right side is entirely in terms of tan theta only.